The solar system floats through space like a small island of warmth in an ocean of endless cold darkness, and when we try to understand its vastness and beauty, we begin to realize how extraordinary our cosmic neighborhood truly is. Here, in this quiet corner of the Milky Way galaxy, a single star burns with steady brilliance, and around that star, 8 planets trace their ancient paths through the void, each one a world unto itself, each one carrying secrets written in stone and ice and swirling gas. The Sun sits at the center of it all, a sphere of incandescent plasma so large that more than 1 million Earths could fit inside its volume, and yet from our perspective here on our small blue world, it appears as nothing more than a bright disk in the sky, warm and familiar, the source of all light and life as we know it. The Sun is not eternal, though it feels that way to us in our brief human lifetimes. It has been burning for about 4.5 billion years, fusing hydrogen into helium deep within its core, where temperatures reach 15 million degrees Celsius, and the pressure is so immense that atoms are crushed together in a nuclear dance that releases tremendous energy. This energy travels slowly outward from the core, taking hundreds of thousands of years to work its way through the dense layers of the Sun's interior, moving through the radiative zone where photons bounce endlessly from particle to particle, then into the convective zone where vast currents of hot plasma rise and fall like bubbles in boiling water. Finally, this energy reaches the surface, the photosphere, where it radiates out into space as light and heat, traveling at 300,000 kilometers per second, crossing the void to warm our faces and power the weather and nourish the plants that feed us. The Sun's light takes about 8 minutes and 20 seconds to reach Earth, which means that when we look at the Sun, we are seeing it as it was 8 minutes ago, not as it is in this present moment. This is true of everything we see in space. We are always looking backward in time, watching light that left distant objects long before we were born, and the farther away something is, the older the light we receive from it becomes. The Sun appears yellow to us, though in reality it emits light across many wavelengths, and if we could see it from space without the filtering effect of Earth's atmosphere, it would appear more white than yellow. Its surface is not smooth or calm, but rather a roiling, turbulent place where magnetic field lines twist and snap, creating sunspots that appear dark against the brighter surrounding plasma, and where enormous loops of plasma called prominences arch hundreds of thousands of kilometers into space before falling back down under the Sun's immense gravitational pull. Sometimes the Sun releases bursts of energy called solar flares, and sometimes it ejects huge clouds of charged particles in events called coronal mass ejections. These streams of particles race outward through the solar system at speeds of hundreds or even thousands of kilometers per second, and when they reach Earth, they interact with our planet's magnetic field, funneling down toward the poles and colliding with atoms in the upper atmosphere, creating the shimmering curtains of light we call auroras. The northern lights and southern lights are reminders that we live inside the Sun's influence within its extended atmosphere, the heliosphere, which stretches far beyond the orbits of the planets, creating a protective bubble that shields us from some of the high-energy particles that pervade interstellar space. Closest to the Sun, at a distance of about 58 million kilometers, orbits Mercury, the smallest of the 8 planets and the one most difficult to see from Earth because it never strays far from the Sun's glare in our sky. Mercury is a world of extremes, with surface temperatures that can reach 430 degrees Celsius on the side facing the Sun and plummet to minus 180 degrees Celsius on the night side. The planet rotates very slowly, taking 59 Earth days to complete one rotation, but it orbits the Sun quickly, completing a full orbit in just 88 Earth days. This creates an unusual relationship between Mercury's day and year, where one day on Mercury, from sunrise to sunrise, actually takes 176 Earth days, or 2 Mercurian years. The planet has almost no atmosphere to speak of, just a thin exosphere of atoms knocked off the surface by solar wind and micrometeorite impacts. And without an atmosphere to redistribute heat, the temperature differences between day and night are extreme. Mercury's surface is heavily cratered, scarred by billions of years of impacts from asteroids and comets, and it resembles our moon in many ways, with vast plains of ancient lava flows and bright rays of ejected material radiating outward from younger impact craters. One of the most prominent features on Mercury is the Caloris Basin, an enormous impact crater about 1,500 kilometers across, created when a large asteroid struck the planet billions of years ago with such force that it sent shockwaves through the entire world, creating jumbled, chaotic terrain on the exact opposite side of the planet. Mercury has a large iron core that makes up about 60% of the planet's mass, and this core generates a weak magnetic field, making Mercury the only terrestrial planet besides Earth to have a global magnetic field, though it is much weaker than our own. Moving outward from the Sun, we come to Venus, the second planet, sometimes called Earth's twin because it is almost the same size as our world, with a diameter only about 650 kilometers smaller than Earth's. Venus orbits at a distance of about 108 million kilometers from the Sun, and from Earth it appears as the brightest object in the night sky after the moon, shining with a brilliant white light. Ancient peoples knew Venus well, and many cultures had different names for it depending on whether it appeared in the morning or evening sky, not realizing it was the same celestial body. Venus is often called the morning star or evening star, though it is not a star at all, but a planet that reflects sunlight so efficiently that it outshines everything else in the night. But despite its beauty from afar, Venus is a hellish world, completely inhospitable to any form of life as we know it. The planet's atmosphere is incredibly thick, about 90 times denser than Earth's atmosphere at sea level, composed mostly of carbon dioxide, with clouds of sulfuric acid that rain down through the upper atmosphere but evaporate before reaching the surface. This thick atmosphere creates a runaway greenhouse effect, trapping heat so effectively that the surface temperature reaches about 470 degrees Celsius, hot enough to melt lead, making Venus the hottest planet in the solar system despite being farther from the Sun than Mercury. The atmospheric pressure at the surface is crushing, equivalent to being almost a kilometer underwater on Earth, and the combination of heat, pressure, and corrosive atmosphere would destroy any spacecraft within hours. Venus rotates very slowly and in the opposite direction from most planets, a retrograde rotation that means the Sun rises in the west and sets in the east, though you could never actually see this through the thick cloud cover. One day on Venus, one complete rotation takes 243 Earth days, which is longer than Venus's year of 225 Earth days. This means that Venus rotates so slowly that it actually takes longer for the planet to spin once on its axis than it takes to orbit the Sun completely. Scientists are still not entirely sure why Venus rotates backward or why its rotation is so slow, though various theories suggest that a massive impact early in the planet's history might have knocked it off its original spin, or that gravitational interactions with the Sun and other planets over billions of years gradually slowed and reversed its rotation. The surface of Venus is hidden beneath its perpetual cloud cover, but radar mapping from spacecraft has revealed a world of vast volcanic plains, highland regions, and strange features unlike anything seen on other planets. There are enormous shield volcanoes, some larger than any on Earth, and vast networks of lava channels stretching for thousands of kilometers. The surface appears to be relatively young in geological terms, perhaps only a few 100 million years old, suggesting that the entire planet was resurfaced by volcanic activity in the relatively recent past, burying older craters and features beneath fresh lava flows. Venus has no moons, orbiting the Sun alone, and it has no magnetic field, likely because its slow rotation prevents the kind of dynamo effect that generates magnetic fields in the cores of other planets. Then we come to Earth, the third planet from the Sun, orbiting at an average distance of about 150 million kilometers, a distance so commonly referenced in astronomy that it has been given its own unit of measurement, the astronomical unit, or AU. Earth is special not because of its size or composition, which are fairly typical for a rocky planet, but because it is the only world we know of that harbors life. Water covers about 70% of the surface, and the presence of liquid water, maintained by Earth's position in what astronomers call the habitable zone, where temperatures allow water to exist in liquid form, has been crucial to the development and sustenance of life. Earth has a substantial atmosphere composed mostly of nitrogen and oxygen, with trace amounts of other gases, including the greenhouse gases that keep our planet warm enough to be habitable. The Earth's atmosphere is not just a passive blanket, but an active dynamic system, constantly in motion, driven by the uneven heating of the planet's surface by the sun. Warm air rises at the equator, cools and sinks at mid-latitudes, creating the circulation patterns that drive our weather and climate. The atmosphere also protects us, absorbing harmful ultraviolet radiation from the sun and causing most meteors to burn up before reaching the ground. Earth's magnetic field, generated by the movement of molten iron in the planet's outer core, extends far into space, forming the magnetosphere that deflects much of the solar wind and protects our atmosphere from being stripped away over time. Earth rotates on its axis once every 24 hours, giving us our familiar day-night cycle, and completes one orbit around the Sun every 365.25 days, which is why we need a leap year every 4 years to keep our calendar aligned with the seasons. The planet's axis is tilted at about 23.5 degrees relative to its orbital plane, and this axial tilt is responsible for the seasons. When the northern hemisphere is tilted toward the sun, it experiences summer with longer days and more direct sunlight, while the southern hemisphere experiences winter. 6 months later, the situation is reversed. Without this tilt, there would be no seasons, and the amount of sunlight each part of the planet received would remain constant throughout the year. Earth has one natural satellite, the Moon, which orbits at an average distance of about 384,000 kilometers. The Moon is unusually large compared to its planet, about 1/4 the diameter of Earth, and this size ratio is unique in the inner solar system. The Moon's origin is still debated, but the most widely accepted theory suggests that it formed from debris ejected when a Mars-sized object collided with the young Earth about 4.5 billion years ago. This giant impact vaporized both the impactor and a portion of Earth's mantle, sending material into orbit that eventually coalesced into the Moon. The Moon's gravitational pull creates the tides we observe in Earth's oceans, causing the water to bulge slightly on the side facing the Moon and on the opposite side. And as Earth rotates beneath these bulges, we experience high and low tides roughly twice a day. The Moon is tidally locked to Earth, meaning it rotates on its axis at the same rate it orbits our planet, so the same side always faces Earth. This is why we speak of the far side of the Moon, not the dark side, because all parts of the Moon receive sunlight as it orbits Earth. The far side, hidden from our view, was a mystery until spacecraft first photographed it in the 1950s, revealing a landscape more heavily cratered than the near side, with fewer of the dark volcanic plains called Maria. The Moon has no atmosphere, no weather, and no erosion except from micrometeorite impacts and temperature changes, so the footprints left by astronauts will remain pristine for millions of years, a testament to one of humanity's greatest achievements. Beyond Earth lies Mars, the fourth planet from the Sun, orbiting at an average distance of about 228 million kilometers. Mars is smaller than Earth, roughly half the diameter, and its thin atmosphere, composed mostly of carbon dioxide, is only about 1% as dense as Earth's. The planet appears reddish in our sky because its surface is covered with iron oxide, essentially rust, giving it the appearance that inspired ancient peoples to name it after gods of war. Mars has the largest volcano in the solar system, Olympus Mons, a shield volcano about 25 kilometers high and 600 kilometers across, so large that if you stood on its summit, the base would extend beyond the horizon in all directions. The planet also has a vast canyon system called Valles Marineris that stretches more than 4,000 kilometers along the Martian equator, up to 7 kilometers deep in places, dwarfing the Grand Canyon on Earth. Mars has seasons like Earth because its axis is tilted at about 25 degrees, very similar to Earth's tilt. But because Mars takes 687 Earth days to orbit the Sun, its seasons last nearly twice as long as ours. The planet also experiences dust storms that can sometimes grow to envelope the entire planet, blocking out the sun for weeks at a time. Mars has two small, irregularly shaped moons, Phobos and Deimos, both of which are probably captured asteroids. Phobos orbits very close to Mars, just 6,000 kilometers above the surface, and it is slowly spiraling inward, destined to crash into Mars or break apart into a ring system within the next 50 million years. Deimos orbits farther out and is gradually moving away from the planet. Evidence suggests that Mars once had a thicker atmosphere and liquid water on its surface, with ancient river valleys, lake beds, and even what appears to be an ocean basin in the northern hemisphere. But something changed billions of years ago. Mars lost its global magnetic field, and without that protection, the solar wind gradually stripped away much of the atmosphere, the planet cooled, and the water either escaped to space or became locked in ice caps and underground. Today, water exists on Mars primarily as ice, in the polar ice caps which grow and shrink with the seasons, and as permafrost beneath the surface. The possibility that Mars once had conditions suitable for life and might even harbor microbial life today in subsurface environments makes it one of the most intriguing targets in our search for life beyond Earth. Between the orbits of Mars and Jupiter lies the asteroid belt, a region populated by millions of rocky objects ranging in size from small boulders to dwarf planets hundreds of kilometers across. Despite its name, the asteroid belt is not densely packed. If you were to fly through it, you would find that the asteroids are typically millions of kilometers apart, and spacecraft have passed through the belt without difficulty. The largest object in the asteroid belt is Ceres, about 940 kilometers in diameter, large enough to be rounded by its own gravity and classified as a dwarf planet. Ceres has a surface of ice and rock, and observations suggest it may have a subsurface ocean of liquid water beneath its frozen crust. The asteroids are remnants from the early solar system, material that never coalesced into a planet, likely because Jupiter's immense gravity stirred up the region and prevented the formation of a larger body. These rocky fragments preserve clues about the conditions and processes that existed when the solar system was forming, and studying them helps us understand our cosmic origins. Some asteroids are made of solid rock, others are rich in metals like iron and nickel, and still others contain significant amounts of carbon and water ice. Occasionally, gravitational interactions or collisions send asteroids into orbits that cross Earth's path. And while most of these near-Earth asteroids pose no threat, some have struck our planet in the past with devastating effects, including the impact 66 million years ago that contributed to the extinction of the dinosaurs. Beyond the asteroid belt, we enter the realm of the giant planets, worlds utterly unlike the rocky terrestrial planets of the inner solar system. Jupiter, the fifth planet from the Sun and by far the largest planet in our solar system, orbits at an average distance of about 778 million kilometers, or 5.2 astronomical units. Jupiter is enormous, with a diameter of about 140,000 kilometers, more than 11 times the diameter of Earth, and it has a mass greater than all the other planets combined. If Jupiter were hollow, more than 1,300 Earths could fit inside it. But Jupiter is not hollow. It is a gas giant, composed primarily of hydrogen and helium, with no solid surface to stand on. If you tried to descend into Jupiter's atmosphere, you would pass through layer after layer of increasingly dense gas, the pressure and temperature rising steadily, until eventually the hydrogen gas becomes so compressed that it behaves like a liquid metal. And deeper still, there may be a core of rock and ice, though we cannot be certain. Jupiter's most famous feature is the Great Red Spot, a vast storm system larger than Earth that has been raging for at least several centuries, possibly much longer. The spot appears reddish, though the exact reason for its color is not fully understood, possibly due to complex chemical reactions in the atmosphere involving phosphorus or sulfur compounds. The storm rotates counterclockwise, and winds at its edges reach speeds of hundreds of kilometers per hour. Jupiter's atmosphere is banded with alternating light and dark stripes, zones and belts, created by powerful wind systems that circle the planet at different latitudes. These winds are driven by Jupiter's rapid rotation, as the planet spins once every 10 hours, faster than any other planet in the solar system. This rapid rotation creates extreme weather patterns and causes the planet to bulge noticeably at the equator. Jupiter has a powerful magnetic field, the strongest of any planet, extending millions of kilometers into space and trapping charged particles in radiation belts so intense that they would be deadly to any unprotected human and can damage spacecraft electronics. This magnetosphere captures particles from the solar wind and from Io, one of Jupiter's moons, which constantly ejects material through its volcanic eruptions. Jupiter has at least 95 known moons and possibly more awaiting discovery, ranging from tiny irregular captured asteroids to 4 large moons called the Galilean moons, discovered by Galileo Galilei in 1610 when he turned his telescope toward Jupiter. These 4 moons, Io, Europa, Ganymede, and Callisto, are worlds in their own right, each with unique characteristics and mysteries. Io is the most volcanically active body in the solar system, with hundreds of volcanoes erupting continuously, spewing sulfur and sulfur dioxide hundreds of kilometers into space. This volcanic activity is driven by tidal heating, as Jupiter's immense gravity squeezes and stretches Io during its orbit, and the gravitational pull of the other Galilean moons creates a resonance that keeps Io's orbit slightly elliptical, maintaining the tidal forces that heat the moon's interior. Io's surface is constantly being resurfaced by lava flows, making it one of the youngest surfaces in the solar system with almost no impact craters because they are quickly buried beneath fresh volcanic material. Europa is perhaps the most tantalizing moon in the solar system from an astrobiological perspective. Its surface is covered in water ice, crisscrossed with fractures and ridges that suggest the ice is floating on a subsurface ocean of liquid water, kept from freezing by tidal heating, similar to but less extreme than what affects Io. This ocean may contain more water than all of Earth's oceans combined, and where there is liquid water and an energy source, there is at least the possibility of life. Europa's ice shell is estimated to be 15 to 25 kilometers thick, beneath which lies an ocean perhaps 100 kilometers deep. The surface shows few impact craters, indicating that it is geologically active and relatively young, with the ice constantly being renewed and reshaped. Future missions hope to explore Europa more closely, perhaps even landing and drilling through the ice to sample the ocean beneath. Ganymede is the largest moon in the solar system, even larger than the planet Mercury, and it is the only moon known to have its own magnetic field generated by a liquid iron core. Ganymede has a mixed surface of 2 types of terrain: dark regions that are heavily cratered and ancient, and lighter regions that are younger and covered with grooves and ridges, suggesting some form of tectonic activity in the past. Like Europa, Ganymede may have a subsurface ocean, though buried more deeply beneath a thicker ice shell. Callisto is the outermost of the Galilean moons, and it has the most heavily cratered surface of the 4, suggesting that it has been geologically dead for billions of years, its surface preserving a record of the solar system's violent early history. Callisto is composed of roughly equal parts rock and ice, and it may also have a subsurface ocean, though this remains uncertain. Moving outward from Jupiter, we come to Saturn, the 6th planet from the Sun, orbiting at a distance of about 1.4 billion kilometers, or 9.5 astronomical units. Saturn is the 2nd largest planet, smaller than Jupiter, but still enormous by terrestrial standards, with a diameter of about 120,000 kilometers, roughly 9 times that of Earth. Like Jupiter, Saturn is a gas giant composed mostly of hydrogen and helium, with no solid surface, and it rotates rapidly, completing one rotation in just over 10.5 hours, which gives it a noticeable equatorial bulge. Saturn's density is so low that it would actually float if you could find an ocean large enough to hold it, the only planet in the solar system with this distinction. Saturn is most famous for its magnificent ring system, the most extensive and complex ring system of any planet. The rings are composed of countless particles ranging in size from tiny grains to house-sized boulders, all made primarily of water ice with some rocky material mixed in. The rings are surprisingly thin, in some places only tens of meters thick, yet they extend outward from the planet for hundreds of thousands of kilometers. From edge to edge, the main ring system spans about 280,000 kilometers, yet if you could view it from the side, it would appear as thin as a sheet of paper. The rings are divided into several distinct sections, separated by gaps where the gravitational influence of Saturn's moons clears out material. The largest gap, called the Cassini division, is about 4,700 kilometers wide and is clearly visible from Earth through a good telescope. The origin of Saturn's rings is still debated. They may be the remains of a moon that was torn apart by Saturn's gravity when it wandered too close, inside what is called the Roche limit, the distance at which tidal forces overcome an object's self-gravity, or they may be leftover material from the formation of the planet that never coalesced into a moon. The rings are probably not as old as Saturn itself and may be only a few 100 million years old, young in astronomical terms. Over time, the rings are slowly spiraling inward, raining down onto Saturn's atmosphere, and eventually, millions of years from now, the rings may disappear entirely. Saturn has at least 146 known moons, the most of any planet, though many of these are small irregular objects that are probably captured asteroids or comets. The largest moon, Titan, is extraordinary, larger than the planet Mercury, and the only moon in the solar system with a thick atmosphere. Titan's atmosphere is denser than Earth's, composed mostly of nitrogen with a small amount of methane, and it is so hazy that the surface is completely hidden from visible light. The temperature on Titan is extremely cold, about -179 degrees Celsius, cold enough that water ice is as hard as rock and methane, and ethane exist as liquids. Titan has lakes and seas of liquid methane and ethane on its surface, the only known stable bodies of liquid on the surface of any world besides Earth. These hydrocarbon lakes are fed by rivers and experience precipitation in a methane cycle, analogous to the water cycle on Earth, with methane evaporating, forming clouds, and raining back down onto the surface. The surface of Titan also shows features that look like river channels, sand dunes, and mountains, shaped by weather and erosion in this alien but strangely familiar landscape. Another intriguing moon of Saturn is Enceladus, a small icy world that at first glance seems unremarkable, but which has proven to be one of the most exciting discoveries in planetary science. Enceladus has active geysers erupting from cracks near its south pole, spraying water vapor and ice particles hundreds of kilometers into space. These plumes contain salt, suggesting that they originate from a subsurface ocean of liquid water beneath the moon's icy crust, and they also contain organic molecules, the building blocks of life. Like Europa, Enceladus is kept warm by tidal heating from Saturn's gravity, and the presence of liquid water, organic molecules, and an energy source makes it another compelling target in the search for extraterrestrial life. Beyond Saturn lies Uranus, the seventh planet from the Sun, orbiting at an average distance of about 2.87 billion kilometers, or 19.2 astronomical units. Uranus is an ice giant, smaller than Jupiter and Saturn, but still much larger than Earth, with a diameter of about 51,000 kilometers, roughly 4 times that of Earth. Unlike the gas giants, which are composed primarily of hydrogen and helium, ice giants like Uranus contain a larger proportion of heavier elements, particularly water, methane, and ammonia, in their interiors, though these substances exist under such high pressure and temperature that they are not in the forms we are familiar with. The methane in Uranus's upper atmosphere absorbs red light, giving the planet its distinctive blue-green color. Uranus is unique among the planets because its axis of rotation is tilted 98 degrees, meaning it essentially rolls along its orbital path with one pole pointing toward the Sun for decades at a time before the other pole takes its turn. This extreme axial tilt results in the most extreme seasons in the solar system. During the planet's 84-year orbit around the Sun, each pole experiences 42 years of continuous sunlight, followed by 42 years of continuous darkness. The reason for this unusual tilt is not known for certain, but it may have resulted from a collision with a large object early in the solar system's history that knocked the planet onto its side. Despite its peculiar orientation, Uranus rotates relatively quickly, with a day lasting about 17 hours. Uranus has a system of faint rings discovered in 1977 and at least 27 known moons, most of which are named after characters from the works of William Shakespeare and Alexander Pope. The largest moons are Miranda, Ariel, Umbriel, Titania, and Oberon. Miranda is particularly interesting, with a surface that looks like it was assembled from mismatched pieces, with regions of different terrain types jumbled together, old cratered plains next to younger grooved regions and enormous cliffs, some up to 20 kilometers high. The cause of Miranda's strange appearance is unknown, but it may have been shattered by a massive impact and then reassembled under its own gravity, or it may have experienced unusual geological processes driven by tidal heating. Neptune is the eighth and final planet in the solar system, orbiting at an average distance of about 4.5 billion kilometers, or 30 astronomical units from the Sun. Neptune is slightly smaller than Uranus but more massive, with a diameter of about 49,000 kilometers, and it is also an ice giant with a similar internal composition. Neptune appears as a deeper blue than Uranus, also due to methane in its atmosphere, but the richer color suggests that there may be an additional unknown component contributing to its appearance. Despite being farther from the Sun and receiving less solar energy than any other planet, Neptune has the most violent weather in the solar system, with winds reaching speeds of over 2,000 kilometers per hour, faster than the speed of sound on Earth. The planet has several large storm systems, including a feature called the Great Dark Spot that was observed by Voyager 2 in 1989, though it had disappeared by the time the Hubble Space Telescope observed Neptune a few years later, suggesting that these storms are temporary features. Neptune has at least 16 known moons, the largest of which is Triton, an unusual world that orbits Neptune in the opposite direction to the planet's rotation, a retrograde orbit that indicates Triton was not formed in place but was captured by Neptune's gravity. Triton is larger than Pluto and has a surface composed of frozen nitrogen, methane, and water ice. Despite being extremely cold, with surface temperatures around -235 degrees Celsius, Triton is geologically active, with geysers that erupt nitrogen gas and dark material high into the thin atmosphere. These geysers are thought to be driven by a kind of solid-state greenhouse effect, where sunlight penetrates the translucent nitrogen ice and warms darker material beneath, causing pressure to build until it erupts. Triton is slowly spiraling inward toward Neptune, and in a few billion years, it will pass within the Roche limit and be torn apart, potentially creating a spectacular ring system around Neptune. Beyond Neptune lies the realm of the trans-Neptunian objects, a vast region of icy bodies that extends outward for billions of kilometers. This region includes the Kuiper Belt, a disc-shaped zone beyond Neptune's orbit that contains hundreds of thousands of icy objects, remnants from the solar system's formation. The Kuiper Belt is similar to the asteroid belt, but far larger and more massive, containing objects made mostly of frozen volatiles like water, methane, and ammonia. The most famous resident of the Kuiper Belt is Pluto, once considered the ninth planet, but reclassified as a dwarf planet in 2006 when the International Astronomical Union created a new definition for what constitutes a planet. Pluto orbits at an average distance of about 5.9 billion kilometers from the Sun, though its orbit is quite elliptical, bringing it as close as 4.4 billion kilometers and as far as 7.4 billion kilometers from the Sun. Pluto is small, only about 2,380 kilometers in diameter, smaller than Earth's moon, but it is a surprisingly complex and geologically active world, as revealed by NASA's New Horizons spacecraft when it flew past in 2015. Pluto has a thin atmosphere that freezes and falls to the surface as snow when the dwarf planet is farthest from the Sun, then sublimates back into gas when it approaches closer. The surface shows a remarkable variety of terrains, including vast plains of nitrogen ice, towering mountains made of water ice as hard as rock at those temperatures, and strange formations that look like giant penitents or blades of ice. Pluto's largest moon, Charon, is so large relative to Pluto that the two are sometimes considered a binary system, orbiting around a common center of mass that lies between them rather than inside Pluto. Charon is about half the diameter of Pluto, and the two are tidally locked to each other, meaning they always show the same face to each other as they orbit their common center every 6.4 days. Pluto has 4 smaller moons, Styx, Nix, Kerberos, and Hydra, all of which are much smaller and irregularly shaped, probably fragments from an ancient collision. Beyond the Kuiper belt lies the scattered disk, a region of space where objects have highly elliptical and inclined orbits, likely scattered there by gravitational interactions with Neptune. One of the largest known objects in the scattered disk is Eris, a dwarf planet slightly smaller than Pluto but more massive, which played a key role in the debate that led to Pluto's reclassification. Eris orbits as far as 14 billion kilometers from the Sun, taking about 560 years to complete one orbit. At such distances, the Sun appears as little more than a bright star, and temperatures are so low that even gases like nitrogen and methane freeze solid. And beyond even the scattered disk, at the very edge of the Sun's gravitational influence, lies the Oort cloud, a vast spherical shell of trillions of icy bodies that extends perhaps halfway to the nearest star. The Oort cloud is thought to begin at about 2,000 astronomical units from the Sun and extend out to perhaps 100,000 astronomical units, a distance so vast that light takes over a year and a half to travel from the Sun to the outer edge of the Oort cloud. The objects in the Oort cloud are the most distant members of the solar system, barely held in orbit by the Sun's gravity, and they are easily perturbed by passing stars or gravitational tides from the galaxy itself. When an object from the Oort cloud is disturbed, it may begin a long fall toward the inner solar system, eventually appearing as a long-period comet, one of those spectacular visitors that occasionally grace our skies with their glowing tails. Comets are often described as dirty snowballs, irregular chunks of ice and rock typically a few kilometers across, and when they approach the Sun, the ice begins to sublimate, turning directly from solid to gas and carrying dust particles with it, creating a glowing cloud called a coma around the nucleus and long tails that stream away from the Sun, pushed by solar radiation and the solar wind. Comets have 2 tails, a dust tail that curves gently along the comet's orbit and an ion tail of charged particles that points directly away from the Sun. Some comets follow very long elliptical orbits that bring them close to the Sun only once in thousands or millions of years before they return to the outer reaches of the solar system, while others, called short-period comets, have been captured into smaller orbits, often by the gravity of Jupiter, and return to the inner solar system every few decades or centuries. The most famous short-period comet is Halley's Comet, which orbits the Sun every 76 years and has been observed and recorded by humans for over 2,000 years. The solar system is not a static place, but a dynamic, ever-changing environment where objects move in complex patterns governed by gravity, where collisions have shaped the worlds we see, and where the Sun's output varies on timescales from seconds to billions of years. All of the planets orbit the Sun in the same direction, counterclockwise when viewed from above the Sun's north pole, and all but Venus and Uranus rotate in this same direction. The planets also orbit in roughly the same plane, called the ecliptic, which is close to the plane of the Sun's equator, a configuration that tells us about how the solar system formed from a rotating disk of gas and dust billions of years ago. About 4.6 billion years ago, in a region of our galaxy where gas and dust had accumulated, something triggered a gravitational collapse, perhaps the shockwave from a nearby supernova explosion. The cloud began to contract under its own gravity, and as it did, it began to spin faster, flattening into a disk with a dense concentration at the center that would become the Sun. The temperature and pressure in this central concentration increased until nuclear fusion ignited, and the Sun was born, entering what is called the main sequence phase, where it has remained for the past 4.5 billion years. In the disk surrounding the young Sun, dust particles began to stick together, growing larger through collisions, forming pebbles, then boulders, then planetesimals kilometers across. These planetesimals continued to collide and merge, and within a few tens of millions of years, they had grown into protoplanets, objects large enough that their gravity began to dominate their surroundings. In the inner solar system, where temperatures were high, only materials with high melting points could remain solid, so the protoplanets were made of rock and metal, forming the terrestrial planets. Farther out, beyond what is called the frost line, where temperatures were low enough for water and other volatiles to freeze, the protoplanets could grow much larger by incorporating these abundant ices, and once they became massive enough, they could capture hydrogen and helium gas directly from the disk, becoming the gas and ice giants. The process of planet formation was violent and chaotic, with countless collisions, objects being ejected from the system, and planets migrating inward or outward as they interacted gravitationally with each other and with the remaining disk material. There is evidence that the giant planets did not form in their current positions, but migrated significantly early in the solar system's history. One model, called the Nice model, after the city in France where it was developed, suggests that Jupiter, Saturn, Uranus, and Neptune originally formed much closer together and migrated to their current positions over hundreds of millions of years through interactions with a disk of planetesimals. During this migration, Jupiter may have moved inward toward the Sun before being pulled back out by Saturn in a resonance, a scenario called the Grand Tack, and this migration would have scattered planetesimals throughout the solar system. Some were ejected to the Oort cloud, some were sent into the inner solar system where they bombarded the terrestrial planets in an event called the Late Heavy Bombardment about 4 billion years ago, leaving the heavily cratered surfaces we see on the Moon and other bodies, and some were captured in the Kuiper Belt and asteroid belt where they remain today. The solar system continues to evolve today, though much more slowly. Planetary orbits shift slightly over time due to gravitational interactions, though these changes are small and predictable over human timescales. The Sun is gradually getting brighter as it ages, increasing in luminosity by about 10% every billion years, and eventually, in about 5 billion years, it will exhaust the hydrogen fuel in its core and begin to expand into a red giant, growing so large that it may engulf Mercury and Venus and possibly even Earth. During this red giant phase, the Sun will shed its outer layers in pulses, creating a planetary nebula, and the core will contract into a white dwarf, a dense, hot remnant about the size of Earth that will slowly cool over trillions of years, eventually fading to a black dwarf, though the universe is not yet old enough for any white dwarfs to have cooled completely. But that is far in the future, and for now, the solar system is a place of relative calm and order, where the planets trace their ancient paths through space, where moons dance around their parent planets, and where the Sun shines steadily, providing the light and warmth that makes life possible on at least one small blue world. The distances in the solar system are so vast that they challenge our comprehension. Light, traveling at nearly 300,000 kilometers per second, takes over 4 hours to reach Neptune from the Sun, and even using our fastest spacecraft, it takes years to reach the outer planets. Voyager 1, launched in 1977 and currently the most distant human-made object, has been traveling for over 46 years and has only recently left the heliosphere, entering interstellar space about 22 billion kilometers from the Sun. Yet, it would still take Voyager over 17,000 years to travel the distance to the nearest star at its current speed. When we look at the solar system, we are seeing a snapshot of a long evolutionary process, a story written in craters and volcanoes, in the composition of atmospheres, and the tilt of planetary axes, in the orbits of moons and the rings around giant planets. Every feature tells us something about the past, about the conditions that existed when the solar system formed, about the collisions and interactions that shaped these worlds, about the physical processes that govern how matter behaves under different conditions of temperature, pressure, and gravity. The terrestrial planets, with their solid surfaces, show us the effects of volcanism, tectonics, impacts, and in Earth's case, the transformative power of life and water. The gas and ice giants, with their massive atmospheres and numerous moons, show us worlds where hydrogen and helium dominate, where storms can rage for centuries, where magnetic fields trap radiation, and where moons can be heated by tidal forces into geologically active worlds. The smaller bodies, the asteroids and comets, the dwarf planets and irregular moons are time capsules, preserving material from the early solar system in nearly pristine form because they are too small to have been significantly altered by internal geological processes. When we study a comet, we are examining material that may have remained largely unchanged for 4.5 billion years. And when we analyze a meteorite that falls to Earth, we can learn about the conditions and processes that existed in the solar nebula before the planets formed. Some meteorites contain tiny grains called pre-solar grains that formed in the atmospheres of other stars and were incorporated into the solar nebula, meaning we can hold in our hands material that is older than the sun itself, stardust in the most literal sense. The exploration of the solar system has been one of humanity's greatest adventures, a journey that began with naked-eye observations of the planets visible from Earth and has progressed through increasingly powerful telescopes to robotic spacecraft that have visited every planet and many of the smaller bodies. We have landed on the Moon, Mars, Venus, Titan, and several asteroids and comets. We have sent probes into the atmospheres of Jupiter and Saturn. We have flown past Pluto and continue to send back data from the outer reaches of the solar system. Each mission reveals new surprises, challenges our understanding, and raises new questions. We have learned that worlds we thought would be dead and inactive are geologically alive, that moons can have oceans beneath their icy crusts, that organic chemistry is common throughout the solar system, and that the diversity of planetary processes and environments is far greater than we imagined. Yet despite all we have learned, many mysteries remain. We still do not fully understand how planetary magnetic fields are generated. What drives the internal heating of some moons? What lies deep within the giant planets? What caused Uranus's extreme tilt? How Saturn's rings formed? Or whether life exists anywhere else in the solar system? We have only begun to explore the outer solar system, with vast regions still unseen by spacecraft and thousands of objects in the Kuiper Belt and beyond that we have only detected as points of light. The search for additional planets beyond Neptune, sometimes called Planet 9, continues, based on strange patterns in the orbits of some distant objects that suggest the gravitational influence of an undiscovered large planet, though such a planet remains hypothetical and undetected. Our understanding of the solar system also provides context for understanding other planetary systems around other stars. Since the first confirmed discovery of an exoplanet orbiting a main sequence star in 1995, we have discovered thousands of planets around other stars, and we have learned that planetary systems are common and remarkably diverse. We have found hot Jupiters, giant planets orbiting extremely close to their stars, where temperatures reach thousands of degrees. We have found super-Earths, planets larger than Earth but smaller than Neptune, a type of planet that does not exist in our solar system. We have found planets orbiting binary stars, planets in the habitable zones of red dwarf stars, and systems with multiple planets in resonant orbits. This diversity teaches us that while our solar system is not unusual in having planets, the specific architecture of our system, with small rocky planets close to the Sun and giant planets farther out, separated by the asteroid belt, may be just one of many possible configurations. The study of our solar system is not just an academic pursuit, but has practical implications for understanding our own planet's climate and geology, for assessing the potential hazards from asteroid impacts, for developing the technologies needed for space exploration, and for searching for life beyond Earth. Understanding how atmospheres work on Venus and Mars helps us understand Earth's atmosphere and climate system. Studying volcanic and tectonic processes on other worlds helps us understand the same processes on Earth. Tracking near-Earth asteroids and comets helps us assess the risk of impacts and develop strategies for planetary defense. And the discovery of potentially habitable environments on moons like Europa and Enceladus gives us targets for future missions that might finally answer the question of whether life exists elsewhere in the universe. The solar system is also a laboratory for testing our understanding of physics. The orbits of the planets provided early tests of Newton's laws of motion and gravity, and the advance of Mercury's perihelion, a small deviation from the orbit predicted by Newton's laws, provided one of the first confirmations of Einstein's general relativity. The behavior of plasma in the sun's atmosphere and the solar wind tests our understanding of magneto-hydrodynamics. The extreme conditions inside giant planets, where pressures reach millions of atmospheres and hydrogen takes on exotic properties, test our understanding of matter under extreme conditions. The formation and evolution of the solar system tests our understanding of how gravity, chemistry, and thermodynamics interact to build complex systems from simpler components. As we consider the solar system in its entirety, we can appreciate both its vastness and its isolation. The distances between the planets are enormous by human standards, requiring months or years to traverse even with our fastest spacecraft. Yet the entire solar system, from the Sun to the outer edge of the Oort cloud, is minuscule compared to interstellar distances. The nearest star, Proxima Centauri, is about 4.2 light-years away, more than 9,000 times farther from the Sun than Pluto. At the speed of light, a journey to Proxima Centauri would take 4 years. With current spacecraft technology, it would take tens of thousands of years. The solar system is an island of warmth and light in a vast ocean of cold darkness, and the planets and moons and smaller bodies are our companions in this isolated corner of the galaxy. The sun will continue to shine for billions of years. The planets will continue their stately dance around it, and the solar system will continue to evolve in subtle ways, shaped by gravity and light and the slow decay of radioactive elements. Collisions will still occur, though less frequently than in the early days. Asteroids will occasionally strike planets or moons. Comets will continue to visit from the outer reaches. Moons will slowly move in their orbits, some drifting away from their planets, others spiraling inward. The magnetic fields of planets may flip their polarity, as Earth's magnetic field has done many times in the past. The Sun's activity will cycle through periods of greater and lesser activity every 11 years, with more or fewer sunspots, more or fewer solar flares and coronal mass ejections. But on human timescales, the solar system seems eternal and unchanging, a stable environment where the same patterns repeat year after year, century after century. And yet, it was not always so. 4.5 billion years ago, this region of space was a chaotic cloud of gas and dust, and in the relatively brief period of a few tens of millions of years, that cloud transformed into a star surrounded by planets. 3.5 billion years ago, life arose on Earth, though we do not know exactly how or where, and over the eons that life evolved and diversified, adapting to changing conditions, surviving mass extinctions, eventually giving rise to complex organisms, to animals and plants, to consciousness and intelligence. For most of the history of life on Earth, no organism looked up at the sky and wondered what those points of light were, but now we do, and we have begun to explore, tentatively at first, sending robotic emissaries to other worlds. And for a brief moment in history, human beings left Earth and walked on another celestial body, an achievement that stands as a testament to human ingenuity and the desire to explore. Looking up at the night sky, it is easy to feel small and insignificant against the vastness of space, but it is also worth remembering that we are part of the universe, not separate from it. The atoms in our bodies were forged in the cores of stars that lived and died before the sun was born. And when we look out at the solar system and beyond, we are looking at our origins, at the materials and processes that made our existence possible. We are made of star stuff, as the astronomer Carl Sagan famously said. And in studying the solar system, we are learning about ourselves, about where we came from, and how we fit into the larger cosmic story. The solar system is our home in the most fundamental sense, the environment that shaped the evolution of life on Earth, and understanding it helps us understand our place in the universe. The planets continue their silent journeys through space, indifferent to our presence, governed by the same physical laws that govern everything else in the universe. Mercury completes its rapid orbit in 88 days, always keeping nearly the same face toward the sun. Venus, shrouded in clouds, bakes beneath its thick atmosphere. Earth teems with life, its surface covered in water, its atmosphere alive with weather. Mars lies cold and dry, a world that may once have been more hospitable. The asteroid belt drifts in its orbit, countless rocky fragments from the early solar system. Jupiter spins rapidly, its great red spots swirling, its many moons circling in complex orbits. Saturn floats in space with its magnificent rings, slowly losing them to the planet itself. Uranus rolls along its orbit, tilted on its side, its seasons lasting decades. Neptune, cold and distant, experiences the fastest winds in the solar system despite receiving the least sunlight. And beyond, in the cold darkness, Pluto and countless other small worlds orbit in the Kuiper belt in scattered disk, while farther still, the Oort cloud surrounds the entire solar system in a vast spherical shell. All of these worlds exist in the same system, warmed by the same star, yet each is unique, shaped by its size, its composition, its distance from the sun, and its history. There are no two planets alike, no two moons alike, and even asteroids show remarkable diversity. Some asteroids are solid chunks of metal, remnants of the cores of differentiated planetesimals that were shattered by collisions early in the solar system's history. Others are piles of rubble, loose aggregations of fragments held together by their own weak gravity. Some are rich in water and organic compounds, primitive remnants of the material from which the planets formed, and each one follows its own path through space, determined by the gravitational influences of the sun and planets, sometimes for billions of years without change, sometimes perturbed into a new orbit by a close encounter. The solar system is not isolated from the rest of the galaxy. The sun and all the planets are moving through space together, orbiting the center of the Milky Way galaxy at a speed of about 800,000 kilometers per hour. Yet despite this tremendous velocity, it takes about 230 million years to complete one galactic orbit, sometimes called a cosmic year. The Sun has completed about 20 orbits since it formed, meaning it has been around the galaxy 20 times, and Earth has been around the galaxy even more times if we count from when it formed. As the solar system moves through the galaxy, it passes through different regions with different densities of interstellar gas and dust, and occasionally it may pass relatively close to other stars, though even these close encounters are typically measured in thousands or tens of thousands of astronomical units, far too distant to have significant gravitational effects. Very rarely, perhaps once every few million years, a star may pass close enough to perturb objects in the Oort cloud, sending some of them falling toward the inner solar system to become comets. There is speculation that some mass extinction events on Earth may be correlated with such encounters, or with the solar system's passage through the plane of the galaxy where the density of stars is higher, though these ideas remain controversial. What is clear is that the solar system exists in a dynamic galactic environment, not in isolation. And over very long timescales, the galaxy's gravitational field influences the solar system's evolution. The Sun itself is slowly evolving even now. Every second, the Sun converts about 600 million tons of hydrogen into helium through nuclear fusion, releasing tremendous energy in the process. This energy takes hundreds of thousands of years to work its way from the core to the surface, and then it streams out into space as light and heat and other forms of electromagnetic radiation. The neutrinos produced by fusion reactions in the core escape immediately, traveling at nearly the speed of light, and billions of them pass through your body every second, almost all without interacting with anything. As the Sun fuses hydrogen into helium, the composition of its core changes, and this changes the balance of forces that keeps the Sun stable. Very gradually, over millions and billions of years, the Sun must adjust its structure to maintain equilibrium, and this causes it to slowly increase in luminosity. When the Sun first formed, it was only about 70% as luminous as it is today, and this has profound implications for Earth's early climate. With less solar energy reaching Earth, the planet should have been frozen, yet we have evidence that liquid water existed on Earth's surface more than 4 billion years ago, a puzzle known as the faint young sun paradox. The most likely explanation is that Earth's atmosphere was different in the past, containing more greenhouse gases like carbon dioxide and methane, which trapped heat more effectively and kept the planet warm despite the dimmer sun. As the sun has brightened over time, Earth's climate has had to adjust, with mechanisms like the weathering of rocks removing carbon dioxide from the atmosphere over geological timescales, maintaining a relatively stable climate suitable for life. In the far future, the sun's gradual brightening will become a problem. In about 1 billion years, the sun will be about 10% brighter than it is today, and this additional energy will accelerate the weathering of rocks, removing carbon dioxide from the atmosphere faster than volcanoes can replenish it. Eventually, carbon dioxide levels will drop so low that plants can no longer perform photosynthesis and the biosphere will begin to collapse. The oceans will begin to evaporate, water vapor will accumulate in the atmosphere, and through a runaway greenhouse effect similar to what happened on Venus, Earth will become uninhabitable. This is billions of years in the future, plenty of time for life to adapt or for intelligent species to take action. But it is a reminder that even our sun, so stable and reliable on human timescales, is not eternal and unchanging. When the sun exhausts the hydrogen in its core, about 5 billion years from now, it will begin to fuse helium into carbon and oxygen, and it will expand into a red giant, growing to perhaps 100 times its current diameter. The sun's outer layers will extend beyond Earth's current orbit, though by that time, the solar system will have changed significantly. As the sun loses mass during the red giant phase, the planet's orbits will expand slightly, and it is possible, though not certain, that Earth might avoid being engulfed, instead orbiting as a scorched, lifeless rock just outside the sun's bloated surface. Mercury and Venus will almost certainly be consumed, vaporized in the sun's expanding atmosphere. The outer planets will receive more heat, and some of their moons might become temporarily warmer, with frozen surfaces melting and atmospheres thickening. But this phase will last only a few 100 million years before the sun sheds its outer layers in a planetary nebula and contracts into a white dwarf. The white dwarf sun will be incredibly dense, packing about half the sun's current mass into an object the size of Earth, with a surface temperature initially exceeding 100,000 degrees Celsius. But without nuclear fusion to generate energy, the white dwarf will simply radiate away its stored heat, slowly cooling over trillions of years. The planets will continue to orbit the white dwarf sun, frozen in permanent darkness, except for the faint light from the hot white dwarf, which will gradually dim as it cools. Eventually, after more time than the current age of the universe, the white dwarf will cool to the point where it no longer emits visible light, becoming a black dwarf, a cold, dark sphere of carbon and oxygen floating through space, orbited by the frozen remnants of its former planets. But these far future events are so distant in time that they seem almost abstract, disconnected from the solar system we know today. For now, the sun shines steadily, the planets orbit in their established paths, and life continues on Earth, the only world we know of that harbors life, though we continue to search for signs of life elsewhere. The search for life beyond Earth is one of the most profound questions in science, and the solar system offers several intriguing possibilities. Mars, with its evidence of ancient water and its subsurface ice, might harbor microbial life, either surviving in protected niches underground or preserved as fossils in ancient rocks. Europa and Enceladus, with their subsurface oceans, are perhaps the most promising locations for life, as water is essential for life as we know it, and these moons have liquid water, organic molecules, and energy sources from tidal heating. Even Venus, despite its hellish surface conditions, has been proposed as a possible location for life in the cloud layers high in its atmosphere, where temperatures and pressures are more moderate, though the sulfuric acid clouds would present a significant challenge for any life there. Titan, with its lakes and rivers of liquid methane, might host a completely different form of life based on liquid hydrocarbons rather than water. A speculative idea, but one that expands our thinking about what life might be and where it might exist. The search for life in the solar system continues with missions planned or proposed to these and other locations, and the discovery of even simple microbial life beyond Earth would be one of the most significant discoveries in human history, fundamentally changing our understanding of life's prevalence in the universe. As we explore the solar system, we are also beginning to think about the future of human presence beyond Earth. The Moon is the most accessible destination, just a few days away by spacecraft, and there are plans to establish permanent human settlements there, using lunar resources to support long-term habitation. Mars is the next target, with several space agencies and private companies working toward the goal of sending humans to Mars within the next few decades. The challenges are immense, from the long journey time of 6 to 9 months to the harsh environment on the Martian surface with thin atmosphere, cold temperatures, intense radiation, and the psychological challenges of isolation. But Mars offers resources, including water ice, that could be used to support human settlements, and its day length of 24 hours and 37 minutes is close enough to Earth's that it might be easier to adapt to than other worlds with very different rotation periods. Looking farther ahead, there are ideas for establishing human presence on asteroids, which could be mined for valuable resources like metals and water, or even on the moons of the giant planets, though the distances involved in the harsh radiation environments near Jupiter and Saturn present enormous challenges. There are also proposals for massive space stations, rotating to provide artificial gravity, where humans could live in space without needing to be on the surface of a planet or moon. These ideas remain largely speculative, the domain of science fiction and long-term planning. But the technologies needed to make them possible are gradually being developed, and the lessons learned from operating the International Space Station and from robotic exploration of the solar system are paving the way for future human expansion into space. The solar system is more than just the collection of objects that orbit the sun. It is a dynamic, interconnected system where gravitational interactions shape orbits, where material moves from one location to another through impacts in the solar wind, where energy from the sun drives weather and geological processes, and where the history of each world is written in its surface, features, and internal structure. Understanding the solar system requires understanding physics, chemistry, geology, atmospheric science, and many other fields, and it requires observations and measurements from Earth-based telescopes, space-based observatories, and spacecraft that visit these worlds directly. Each new mission, each new observation adds to our knowledge, filling in details and sometimes overturning previous assumptions. The exploration of the solar system has also inspired people, capturing the imagination of scientists and the public alike. Images of distant worlds, from the swirling clouds of Jupiter to the cratered surface of the Moon, to the rings of Saturn, to the icy plains of Pluto, are not just data, but works of art, revealing the beauty and diversity of the worlds that share our cosmic neighborhood. These images remind us that we are part of something larger, that our small planet is one member of a family of worlds, and that the universe is filled with wonders waiting to be discovered. The desire to explore, to understand, to push the boundaries of knowledge is a fundamental part of what makes us human, and the solar system, vast as it is just the beginning of that journey of discovery. As the planets continue their eternal dance around the sun, as comets swing in from the outer darkness and asteroids tumble through space, as the sun shines with its steady light, we continue to watch and study and learn, piecing together the story of the solar system, understanding how it came to be and how it works and what its future holds. We are still in the early stages of this grand exploration, with much left to discover, but we have come far from the time when the planets were mysterious lights in the sky, moving against the background of stars in ways that puzzled ancient astronomers. Now we understand that they are worlds, each with its own characteristics, governed by the same physical laws that govern everything in the universe, and we have sent our robotic ambassadors to visit them, extending our reach and our senses across the vast distances of space. The solar system is our home, the environment that has shaped everything we know, and it will remain our home for the foreseeable future, even as we begin to explore it more extensively and perhaps establish human settlements on other worlds. Understanding the solar system is understanding our context, the cosmic address where we reside, and it provides perspective on our place in the universe. We are inhabitants of a small planet, orbiting an average star in a typical spiral galaxy, one of hundreds of billions of galaxies in the observable universe. Yet this small planet is the only place where we know life exists, and it is precious beyond measure. The solar system is not just a collection of objects to be studied, but the stage on which the drama of life has unfolded, at least on one world and perhaps on others as well. The sun continues to pour its energy into space, bathing the planets in light and warmth, driving the processes that make Earth a living world and shaping the environments of all the other planets and moons. The solar wind streams outward, carrying the sun's magnetic field with it, creating the heliosphere that surrounds the solar system. The planets orbit, each in its own rhythm, Mercury completing more than 4 orbits in the time it takes Earth to complete one, while Neptune requires more than 160 Earth years to complete a single orbit. The moons orbit their planets, dozens of them, each world with its own character. The asteroid belt drifts between Mars and Jupiter, and the Kuiper belt extends beyond Neptune, and the Oort cloud surrounds everything, a vast reservoir of icy bodies that may number in the trillions. This is the solar system, a small corner of the universe, but infinitely rich in detail and complexity, a place where worlds of rock and ice and gas exist in an intricate dance governed by gravity and light, where the story of planetary formation and evolution has played out over 4.5 billion years, where life arose and evolved on at least one world, and where we, the inheritors of that long evolutionary process, have developed the ability to understand our surroundings and to venture beyond our home planet to explore our cosmic neighborhood. The journey of discovery continues, and with each new mission, each new observation, each new analysis of data, we add to our understanding of the solar system and our place within it. The solar system exists in the present moment, but it carries the weight of billions of years of history, and it will continue to exist and evolve for billions of years into the future. It is a testament to the creative power of natural processes, to the way that gravity and chemistry and thermodynamics can transform a cloud of gas and dust into stars and planets and moons, into worlds with mountains and valleys, with atmospheres and magnetic fields, with seasons and weather, and in at least one case, with life. As we drift towards sleep, we can imagine the solar system continuing its quiet existence in space, the planets following their ancient paths, the sun shining steadily. And in that vastness and silence, we are reminded of the beauty and mystery of the universe we inhabit, a universe that continues to reveal its secrets to those who seek to understand it, one discovery at a time, one world at a time, one question at a time.